Hey guys, you're watching Python tutorial videos on my YouTube channel Python for Microscopists. This is a continuation of the previous tutorial where I introduced or provided an overview of deep learning and neural networks. So here we're going to do some coding, to apply, to write or to build our convolutional neural network, train it for detecting parasitic blood cells versus healthy cells. Okay. Now, just before jumping on to the topic, just a quick overview of how serious this problem is. And you probably heard Bill Gates talk about this, but malaria is a pretty big deal in most tropical countries. Uh, I heard a few people look at this slide and explain this as malaria is a serious problem in third world countries. Like, come on, look at the map. These are all tropical countries, okay? Third world or not. So do not insult people and countries by labeling them as third world or whatever. Anyway, sorry, I don't want to deviate from the topic, but coming back to the topic, of course, it's a big deal. A lot of people are dying, and in fact, the early symptoms would be like fever, for example, but it can turn very deadly if proper treatment is not given in a timely manner. So how do they diagnose this to begin with? Believe it or not, in most places, this is a manual counting of these parasitic blood cell images under a microscope. Right? I mean, so under a microscope, you put these bloods, and then someone is actually manually counting these parasitic blood cells. Obviously, the accuracy depends on the human expertise. And of course, it can be time consuming. If you're paying the human, if the incentive is some sort of number of images per unit time, then of course someone wants to go through these images as fast as they can. So it's not an ideal way. It's not a repeatable way or more accurate way of diagnosing this very serious disease. So I'm not saying we are going to cure malaria in the world by via deep learning, but this provides a great use case. Of course, it helps us understand the problem, and also so we can actually go and write code for this. So deep learning can definitely be used to automate the process. So in the tutorial, let's put together a Python code for convolutional neural network, and that we are going to train using the infected and uninfected cell images. Okay, and the images can be obtained from, in fact, I mean, I put the URL up there. I can show you. So this is the place. Like I went to National Library of Medicine and malaria datasets. If you Google search for this, it's easy for you to find and just download the cellimages.zip. This is exactly what I've done, cellimages.zip. And the way the folder structure looks like, so under cell images, when you unzip it, it unzips into two subfolders. One is parasitized and the other one is uninfected. Okay, so when you open the parasitized, it contains 13,779 images. Okay, and they're all cropped from what appears to be a larger region. So each image comes in different size. Okay, so this one is 151 by 100, and the next one seems to be 148 by 148, and then we have something that's 109 by 115. So each image is different, so obviously we're going to resize it as step one. Okay, we'll get to that in a minute. So uninfected, exactly the same number of images. Okay, so which makes it great because it helps us balance the data sets. Sometimes obviously what you don't want to have is 10,000 15,000 images for parasitized and then only like 500 images for uninfected. Then it's not balanced enough. Of course, we can do some tricks, like we can do some data augmentation. If I have time, I'll create a video on data augmentation to kind of add more images by transforming or morphing the images that you have. But for now, let's not worry about it. We have parasitized and uninfected right here. Okay, so let's jump in. So this is where you can get the data from, and let us go ahead and start writing our code. Well, the first thing to do is to make sure you have installed TensorFlow and Keras. Yeah. So Keras runs on TensorFlow, well, or Theano, but I'm gonna work with TensorFlow. So make sure you have them installed by just testing import Keras. Obviously, if it's your workstation, you would know if you have installed Keras or TensorFlow. If you have never done that, well, you can always go Google search and type pip install pip install TensorFlow. I was searching for GPU, but just TensorFlow, let's say, and then it takes you to a page where it talks about how to install, TensorFlow. And I believe it is just pip install and then TensorFlow. Unless you want the GPU version, then you can just do the GPU. Same thing, pip install Keras. I think it's just Keras with uppercase K. So you can go yeah, it's the Keras with uppercase K. That's pretty much it. Okay, so once you have those ready, then I believe you are ready to start coding because everything else that we would be importing, hopefully you have them already installed, like NumPy and OpenCV and Pillow and so on. So starting with NumPy as NP. Okay, this is the first library I typically import, and the other one I import is OpenCV, CV2. And because I want to walk through some folders, I can either use glob or I can use functionality from OS, os.list directory. So I can actually look at the directory names and so on. So let's go ahead and do import, go ahead and import OS. And what else? Oh, by the way, I totally forgot. So while we are doing NumPy, let's actually set the np.random.seed to some number. And the reason I'm doing this is there are like some pseudo random number generators. I'm fixing that at a fixed value right now because this enables you to get repeatable results every time because these random numbers are used in the background to actually generate something, right? I mean, you'll see as the code progresses. So every time you run the code, you don't want different results. If you're trying to understand the implications of adding a convolutional layer or deleting something, you want to interpret the results by not changing the experiment by a lot. So by setting the random number to a specific value, then or a specific seed, I should say, then at least you guarantee that, okay, one less variable to worry about. Okay, that's the reason I'm just setting this variable, the seed, right now. Okay, um, at some point we need to resize the images. We just talked about it. We have a whole bunch of images, different sizes. We need to resize them. And the easiest way to resize images is using image.resize from Pillow. So what I'm going to do is from PIL import image. Okay, so this can help us actually convert an image into a or a numpy array into an image and then resize it and then convert back into numpy array. Okay, again, there are many ways to resizing your images. It's up to you which library you would like to use. Oh, what else? Oh, of course we forgot the main one, Keras, import keras. Okay, now, every time I import Keras, I like to define os.environ environment, and our Keras environment is what is the backend, right? Underscore backend. So my backend is TensorFlow. So I'm going to just say, sorry, my backend is equal to TensorFlow. There you go. Okay, so otherwise you can also set it to Theano if you want, but like I said, I like to use TensorFlow. It's newer. Uh, okay, so what do we do next? Next, we can actually start looking at importing our images, resizing, and all of that. But before doing any of that, let's actually think about what are we trying to achieve. Well, we're trying to segment a whole bunch of uninfected and infected cells, and we're trying to train an algorithm. So in future, we can look at new images, and the algorithm can basically, with certain confidence, say that, okay, this is an infected or uninfected cell, right? So how do we design our network, right? So the file handling and everything, we'll get to it in a minute, but I don't want to spend a bulk of time talking about it. But let's actually look at how do we design our network. Okay, so again, if you watched my previous tutorial, you understand that, okay, part of the network, the toolkit that we have is the convolutional side of it and the deep, the dense side of it. Okay, or the dense. So the convolutional side is basically the convolutional layer, the pooling layer. Of course, we can add some normalization and dropouts, while we are doing that. And on the dense layer, on the hidden layer, we have, dense layers that we can actually define. And somewhere in between, of course, before the data gets handed off, we need to flatten the 2D into 1D array, so the dense layers can actually propagate through this. The data can propagate through these dense layers. Okay, so how do we design that? Again, let's go back to the drawing board and let's actually see. Okay, initially I have my input. So let's say this is my input layer. So I need to start with, okay, what's my input, right? And then let's do one convolutional. So let's actually do convolutional layer one. Okay. You can add any number of these. So, and after this convolutional, I want to add max pool. Okay. And then let's do max pool one. And then let's also add another convolutional and then another max pool, right? Another convolutional, another max pool. You can go, I mean, you can actually add any number of convolutional and max pool. And in fact, you don't even, let's say if you want, you don't even need to go into the dense layer part, in which case it's called a fully convolutional network. Okay, so we're not building a neural network. In that case, it's called a fully convolutional network. And these are convolutional max pool. And in between, let's do something to our data to make sure. First of all, let's actually do some sort of a normalization here. Okay, so this layer is normalization. Uh, the pen doesn't want to write right now, but anyway, the next one, let's actually include some dropouts to minimize any overfitting. Okay, so this is a dropout right there. So this is one thing, and then let's repeat that one more time. So this is like one convolutional, this is the second time. And now what shall we do? Let's actually stop at that point and then flatten the data. Okay, and once we flatten this, then we can actually go and start defining our dense layers. Okay, so I'm gonna, I hate changing these colors, but okay, makes it easy. Okay, so now let's actually do pretty much the same thing. A couple of one dense and then another dense layer and apply some sort of uh, okay, so dense here and then pretty much the same thing. Let's do normalization and dropout. Again, I chose to change color, so let's do that again. So again, these two, one normalization, one dropout. After this, one normalization and one dropout. And I think let's experiment with that. Okay. After that, let's go ahead and create our output. Yeah, define our output with an activation of sigmoid. Okay, for now, let's just do sigmoid. Again, watch my previous video in terms of the choices of these activations. And then we can define our model. And as part of the model, again, I'm going to use Adam as optimizer. And as a loss function, let's use cross entropy. Okay, and again, if you want to get more, I mean, if you don't know what I'm talking about, watch my previous tutorial. I literally covered these topics there. So let's define this, starting with the input. Okay, so instead of wasting time typing, I mean, instead of wasting the video time where you watch me type, I actually put it on my notepad right here. Let me copy it and paste it, and then we can actually look at each and every line in a second. Okay, so yeah, I changed this. I mean, I have some personal notes here because I did not define a size. Let me type 64 by 64 for now. Okay, I'll explain this in a second. I put a note to myself that, okay, define something called size, so it's easier for me to change the shape every time rather than coming to the code and editing. But ignore that part for now. Okay, so let's go through these again. I explained this in the previous tutorial, but it's worth mentioning one more time. So initially, my input shape is 64. I'm defining my shape 64, 64, and 3. Okay, these are the input images that are actually going into this network. Okay, which means when I add a bunch of line of code, let's actually put right there. Okay, I'm going to separate this. So here I'm going to add a few lines of code later to read the images and resize them into 64 by 64 by 3. Okay, so we'll do that in a minute. But once those images are ready, the input shape is defined here. Okay, and my input layer is keras.layers.input. And by the way, there are many ways you can actually, well, actually, there are two primary ways you can define your the way you define your network. Okay, this is one way where I define each layer by labeling it, by naming it, by calling it convolutional layer 1, pool 1, normalization 1, and drop. And then let's do convolutional layer 2, pool 2, norm, and drop. And then I want to flatten it. So it maps very well with what I want to do. Input, convolutional 1, max pool 1, normalize dropout. Same thing, repeat. And then flatten the data. And then get to the dense layers. Okay, so that's exactly what I'm defining here. And it's very easy, as you can see. Just single line for each of this layer, and then you define your kernel size, because convolution is nothing but a kernel is convolving with your input, whatever that input is, and you need to define the pixel size, I mean the kernel size there. And activation is ReLU that we will be using. So, and after the flattening, we have a hidden layer and normalization and drop, hidden layer 2, normalization and drop. So this is basically repeating twice. And one thing you can see is for every step, when I start with input, I'm defining my input, right? And then my convolutional 1, this is the line where I'm describing what the convolutional 1 is. And then right next to it, the INP is the name of the previous layer. So in this example, it is input INP. Okay, so if I go to pool 1, okay, what do I want to do? Pool size 2 by 2, and again, what it does is it puts a 2 by 2 matrix on top of the previous image, right? Which image? Convolutional 1, or this data set, if you want to call it. So on top of that, it's actually putting 2 by 2, and then it's pulling the maximum number. So within that matrix, what is the maximum number? And it's actually giving an output. Now, once we have that, then I'm going to normalize it and drop out 20% of my data. Okay, randomly. And that is again a way of regularizing my algorithm, so I don't do overfitting. Well, at least I minimize overfitting. So once that's done, the next convolutional block starts, and this is again taking the previous input and so on. Okay, I like this way of defining the layers. Now, there is another way of defining layers, and some people like it because it makes, again, it's an easy way. So the way I think I also copied that somewhere. Let's go ahead and copy and paste so I can show you exactly how it looks like. Okay, and again, if you can go to, you can Google search for convolutional neural networks online, and you can actually see it. So here. I define my model, and then I actually use this sequential model. Okay, so right there, this is I believe this is from Keras, and it makes our life easy in defining these. Okay, and now we can just pass a list of layer instances to this constructor. That's it. Okay, so once we define this as sequential, then I can just go ahead and say, okay, model dot add convolutional 2D. Okay, and 32, 3, 3, and size 3. This is nothing but my 64 by 64 by 3, right? And then define max pooling 2D, and then batch normalization drop out 20%. This is exactly same as what I have defined here. Convolutional with a size 32, kernel size 3 by 3 ReLU, and same thing down here. Okay, convolutional 32 3 by 3 input shape, and then my activation is ReLU, and so on. Okay, so this is exactly, I mean, this is another way of defining what we have defined up there, except slightly different format. There you go. Okay. So to flatten, it's just that model.add flatten. So I just here pretty much the same thing, keras.layers.flatten, and add the dropout. Looks like in this case, I just called it batch normalization, dense and flatten because I imported everything from Keras, but here I'm just doing keras.layers. Okay. Anyway, so this is a different way. And let's go back and then look at our code. Okay. So I just showed you a different way to do things to define the network. Now, I hope this makes sense. And up to the drop 4, and then my output layer is where again I'm defining this as part of keras.layers.dense with a number of units as 2, and activation is sigmoid, and then it's applying on to the last output that's coming from this network. And once I have it, then my model, I'm going to create an instance for my model calling keras.model, and my inputs is nothing but INP, right? I mean, this is our input right there, input layer. And then the other argument it takes is obviously the output, which is the output layer here. Okay, and now I'm going to compile the model using an optimizer called Adam. Again, I talked about this in the previous lecture. And what is our loss function that we are trying to minimize? After every epoch, this is categorical cross entropy. I mean, it's categorical is just one of the variations of cross entropy. I believe the one of the other ones is called binary cross entropy. But anyway, as long as it's up to you which one you want to use. But let's use this one for now. Okay, so this is what we defined, and we can print model summary. Okay, so let's go ahead and run this. And it's going to print, let me expand this side so we can see it a bit better. Let me move this up. There you go. And here, so this is the summary, which is my layer, output shape, and parameters. This is one way of kind of doing your sanity check. Did I do everything right? My input layer, 64 by 64 by 3. Yes, that's exactly what my input images are going to be. My convolutional 2D layer, 64, 64, 32, and we can check that. Okay, so there you go. That's the 32 right there, which means there will be 896 parameters in this layer. And then the next one, max pooling, obviously no parameters, we are just max pooling it. And then comes batch normalization, and here we have 128 parameters. Convolutional 2D, the next set we have 9,000 parameters, and each time, once you get into the dense layer, there is I don't even know how many, 4,194,816. So when you add all of these, then finally, I mean, this is the output layer, sorry, before moving on. So you have like two outputs coming, and the total parameters are these many, and total trainable parameters and non-trainable parameters are these many, right? So now we have these many trainable parameters. So every time it actually goes through these iterations and batches and epochs, it's actually training on these many parameters. So that's why you need very good computation. And I'm not even talking about multi-threading yet, but at some point you have to put everything that you see here, for example, in some sort of a function, and define multi-threading and let the multi-threading take care of distributing the work between the cores that you have in your system. I'm just showing this on my Dell laptop, so it's not going to be a powerful laptop. So I'm not doing, I mean, even if I do multi-threading, I have only 4 cores, and I need at least 1 core to record my video, for example, the one I'm doing right now, and 1 other core for something else. So anyway, uh, at this point, I hope it makes sense in terms of how to define the layers, and everything else is bookkeeping now. I mean, I said in one of the previous videos, in most of the videos, I talk about how it is very important, for us to spend most of the time handling the data. Yeah, if the data is clean, then you get very meaningful numbers out. Otherwise, garbage in, garbage out, right? Okay, so now let's define a couple of ways. Well, let's resize our images to 64 by 64. So let us start by defining our image directory. So our image directory is image underscore directory. My image directory is going to be cell underscore images, right? So this is where I have all my images. In fact, for this video purposes, I took 1,000 of these images, like 500 infected, 500 uninfected, and then placed them in a separate folder called cell images 2. So let's use that for this video purposes. And hopefully I'll run the other one, the full data set, and we can look at the results later on. But cell images, so I defined that. Now, my input shape, I don't want to hard code those numbers. So let me define something called size. And my size right now, I'm going to fix it to 64 so I can change this to size. That's exactly my notes right there. Okay, so now I changed it to size. And what else do we need to define? So now uh, we will be reading in images, which is again nothing but numpy array. So you can store them in a, for example, in a list of numpy arrays. You can create an empty list and we can populate it with all the numpy arrays, each numpy array corresponding to an image that we are reading. Or you can create a data frame using pandas data frame, to hold all your data. It's up to you how you want to handle. Either way, it's fine. So let's actually start by defining an empty list and use this approach. Okay. And so this is where my entire data set is going to be residing. So all of my 1,000 images, each image, a NumPy array is going to be populated inside this data set. Now, we have to assign a label to these, right? So one folder is infected, the other folder is labeled as uninfected. So let's assign a label of 0 to infected ones, or parasitized. I think that's the folder name. And let's assign a value of 1 for the label to the uninfected ones. So the best way to do that is, again, I'm going to create an empty list for my labels. So for every image, I'm going to assign a label of either 0 or 1. Yeah. So now we can go ahead and start reading our images and let's start by parasitized image. Okay, parasitized underscore images equal to os dot, let's list, where is it, list dir, and where is it located, images underscore directory, right? Images directory, and within that they are located in a subdirectory called parasitized. Okay, so parasitized, that should work. And oh, it's image underscore directory, right? So yeah, that should do. Okay, so my parasitized image directory is right here, and now I need to iterate through every file within that subdirectory. So for I, and also let's do image name in enumerate. Okay, and enumerate, remember, it's the enumerate method adds a counter. Okay, so what do I want to enumerate through? So parasitized images, the one we just defined above. Okay, so for these images, like for every image, okay, in parasitized image, okay, enumerate, of course, assigns a number. What do we want to do? If the image ends with png, I think all of our images end with png, but we can go ahead and define that. If image underscore name, let's split the name at what? At the period. Okay, so let's split the name right there. Okay, I forgot this. Okay, so and look for png. If this is equal to png, right? Let me go ahead and look at this code once. If image name is png, and this is where we make most of the mistakes, at least I make most of the mistakes. Okay, then what do we want to do? My image is, let's go ahead and start reading this. Okay, if the extension is png, read it. So cv2.imread, and image underscore directory, right? So image underscore directory is cell images 2, and slash, well, we called it parasitized, parasitized, okay, within that folder, look at image name, right? So again, for image name right there. So we need to add that here. So all we're doing is going through each image in the folder. Okay, first of all, we are checking, is that a PNG extension? If so, read the image. Okay, and now we just need to resize. And one easy way of resizing is let's actually convert the image into PIL, into the PIL format. So image dot from array, because we are reading it from a numpy array. Our original image is numpy array now because we used OpenCV to read it, and the image is RGB. Okay, so now I defined my image as from array image. Okay, that's good. Now we can go ahead and resize it. Okay, so image equals to image dot resize. This is why I converted that to numpy array, and to what size? Size. So this makes it easy for us to resize it to different sizes easily because we defined this size parameter up there. Okay, so now so now that we have it, so what do we want to do? We want to convert this image back into a NumPy array and add it to the data set. We can achieve that in one line. Dataset dot append. What do we want to append? This NumPy array, right? So np dot array of your image. I think this should work. Label dot append, and let's append 0 to every image. Okay, so again, there are many ways to do this. This is the way I chose to do it, okay, to resize these images. So for I and image name, in enumerate parasited images, so under this folder, go through every image, see if it is a PNG. If so, go ahead and read it, okay, and this is my file name, and convert that image, right? This image that we just read into the code, convert that into this PNG file, because it's easy for me to resize PNG file. So I'm using this and resizing it into 64 by 64, and then convert that back into a NumPy array and add it to the dataset list, and do the same with the label. Go ahead and append a value of 0 to each image that we are reading in here. That is it. Now, instead of typing the whole thing again for uninfected, let me copy and paste this and change every parasitized into uninfected. And here, these are, let's say, uninfected, which means I need to change this up here. It's easy to make mistakes when you copy. Sometimes you just have to type it from scratch, but let's see, uninfected, and I think we should be good now. Oh, label.append 1, or uninfected should be 1. So it's going to up here, it's going to take care of parasitized images. Down here, it's going to take care of uninfected images, and I think we are okay. Let's go ahead and run this. Okay, so we should see, I mean, it may take a little while, but there you go. So that means everything is working okay. Okay. Now what? So we resize the images, and the images are actually going in, well, and then we defined, hey, so, as of now, nothing is happening in between, I mean, the images and the network that we just defined. So the next step is we need to apply this convolutional network. You know, we need to define a model and then train this model and so on. Okay, how do we do that? Well, as we learned from our previous tutorials, the first step is always divide the data into test set and training set. So let's start by splitting the data into testing and training set. Well, we have done this task many times in the previous video, so I'm going to copy and paste it from one of the previous tutorials, and there you go. And let me move this away so you can see the full line. So again, we are using scikit-learn model selection test train split, and I'm splitting it into x and y, x train, x test, y train, y test, and our input is obviously the data set that we defined up here. So this is the input, the list of all NumPy arrays, and two categorical NP NumPy array, and looking at the labels, and that is my and the test size is going to be 20%, which means say I have 80% of the data for training, and I fixed random state to 0, or you can put any number there, 200 or some number. And again, the need for fixing random state is I don't want results changing every time. I don't want it to pick up different training and testing data sets every time we run the code. So once we have this, now I can go ahead and fit the model. And the way we fit the model is give it a name. It's traditional for convolutional neural networks to call it history. Let's say, okay, model.fit. Again, this is nothing new. Model.fit is something that we use whether we did traditional machine learning or deep learning. Okay, so the first thing is what is, or what are our x and y values. So the first one is x underscore train. Okay, now let's convert that into an NP array. Okay, x train. Let's see. And then what's our y? Y is our y underscore train. Okay. And now we can divide this into various batch sizes, even though I only have 500 images in each folder. Now, I don't like to load all those 500 images into the memory. I want this to work with batches of images. So let's actually do batch size equal to 64. So it takes 64 images at a time. And verbose equals to 1. And let's do how many epochs? Let's do 25 epochs. Again, just to define, one epoch is when it actually goes through the entire data set once through the network and also back the network. Yeah, feed forward and back propagation. So both one epoch. So let's do 25 and see uh, how it works. Let's actually also do validation split, and let's do 10%. Okay, 0.1. So what it does is, again, it holds out 10% of the data for validation, so we can actually monitor how the validation accuracy is progressing. And shuffle, otherwise by default I think it shuffles, so let's just go ahead and say false. uh, that's it. So we defined our model, and now we can go ahead and run it. Uh, but then let's print out something so we can keep an eye on what's going on. So we can print out the test accuracy. So again, I've written some lines, so I don't want to write code showing you how to plot them. So let's go ahead and paste it. So again, all these lines are doing is basically I'm printing the test accuracy by looking at model.evaluate and looking at the x test and y test. Okay, again, we have done this once in the as part of random forest, and also probably as part of other tutorials. So this is nothing new, and I'm multiplying that value by 100 so I can actually print out the percentage, and rather than just looking at 0.8 or instead of 80%. That's pretty much it. And then here we are defining what is it saying, PLT, uh, PLT, undefined name PLT. Didn't we import matplotlib.pyplot as that's a library that we need to import. So import matplotlib.pyplot as PLT. Okay, so now that should be good. So now we are all I'm doing is actually printing out the performances, like the convolutional neural network performance, and also I'm printing out the from the history, the validation accuracy and training accuracy. Okay, if you want to look at the code, go ahead and look at it. But this is nothing but basically plotting the parameters that we are unwrapping out of our history, out of our model.fit up there. And of course, I also want to plot these against epoch, so we can actually see how values change after every epoch. Okay, so that should be fine. And while we are at it, why not just go ahead and save the model so we can go ahead and use it later on other data sets if we want. So model.save, let's say, what shall we call it? Malaria underscore cnn dot h5. So, okay, so this is our model save. So let me zoom out a bit, and then so we can get a big nice view of what the plan is. Okay, before running this, let me quickly summarize it. I mean, the video is getting long, but it's worth actually doing a sanity check before we start running the code. So we are importing the required libraries with by specifying a random seed up there, and then I put a placeholder for dataset and label placeholder empty lists, and basically filled these empty lists by resizing the images and filling them with corresponding NumPy arrays, and also the same down here. And in fact, when we did our initial run, you can actually see that this data set has 1,000 entries. Okay, 500 for parasitized and 500 for uninfected in this folder, and 1,000 entries, and each one is a NumPy array. Okay, it's basically a list of bunch of NumPy arrays. And my label is also a numpy a list with 1,000 entries. The first few entries, as you can see, are zeros, and they are zeros because we said, okay, all the unparasitized ones should be appended with a label of 0. Okay, and then what do we see? We went down, looked at the image. I mean, we resized it, and then we defined our network. And again, you can look at the network here by printing it out. So we just printed the network, and we split our data into train and test, and then we are feeding the training part into the model down here. Okay, and I think we're okay. So we defined this model, and we are feeding it. Yeah, taking the model and printing out our text accuracy, and then everything else. So let's go ahead and run this. Okay, sorry for going through this one more time, but this is a sanity check. So right now it's resizing all the images. That was pretty fast because it's only 500. Okay, and next step is going to be training the model, and then hopefully we should see some printouts in a minute. Uh, oh, even obviously, it spits out. This is one thing I like about Keras. Uh, so let's see. So for epoch 1 out of 25, it's going through each image. And why is it 720 images? That's because we have, yeah, we split our 1,000 into 20% there. And of those, it's actually holding out, I believe, 10% for validation. So it's 720 images. Okay, there you go. So now let's try to understand the results. So let me expand this part a little bit, and also right there. So you probably saw that it's going through each epoch, and then it's doing 720 images. And again, that's nothing but it's got 800 images for training and 200 images for testing that we intentionally held out. And then within the 800 images, it took 10%, somewhere we defined, yeah, validation split. It held out 10%. That means 80 images, and which leaves 720 images right there. So 720 samples and validate on 80 samples. In fact, I could have actually run this. There was probably no need to split my initial data set into train and test, but that's okay. So this is it went through each and every one of these images, and the loss here is the the value for this loss function is 0.69. This is what it tries to minimize. Okay, and remember the loss function that we are using here is, if you remember, it is categorical cross entropy. Okay, so it's trying to minimize that, and the accuracy is 63.75%. Well, actually, yeah, the accuracy after this epoch is that, and the validation loss is this, and the validation accuracy is 56. Keep an eye on this accuracy. This is the training accuracy, meaning the accuracy on the training data set, and this is the accuracy on the validation data set. Okay, and the training data set accuracy improved and improved and improved and improved, keeps on improving, which is great, but our validation accuracy remained the same, did something. In fact, instead of doing that, I just chose to plot it. So the total test accuracy, the final test accuracy, is 80.5%. Now, if you look at these plots, the accuracy, so you see the blue line here. I could have increased the font size or image size there, but the blue line here is the train accuracy. Okay, the accuracy on the training data set, and it's approaching 1, which means it's doing amazingly well on the training data set. And how is it doing on my validation data set? Horrible. It's jumping up and down, up and down. It wants to settle down at some point, right? But it's not there yet. That's because maybe we can increase this to 100 epochs and see if something happens there. Okay, and if you look at this is a good sign actually here. Again, if you look at the training loss, starts off high, but then it kind of gets better saturated. Okay, so the loss function. Validation loss is also seems to be converging, like it's getting down, but still jumpy, but then it's trying to getting down. That's a good sign. It wants to converge. Okay, so it's not just going all around. So again, this is classic example of overfitting because it's working great on the training data set, but not great on the test data set. Okay, so both of these. Ideally, the training and the testing eventually would converge, would be very close to each other, which tells us that the model that we actually just came up with is a good generalized model, meaning it's ready to see other images, any images. So it's ready to be deployed. This is not ready. And one of the primary reasons, well, two reasons. One, number of epochs, but I bet I can increase the number of epochs to 100, 200, 1000. I may still not get very good accuracy. I may be saturated at 85 or something, maybe 90. It's a good test to do, but not on my laptop. The primary reason being, I would say, the number of training images are only 720 right now, right? I mean, that's the number of training images. If I used the original data set that had more than 10,000 images, then I bet this will convert. So what I'll do is, again, I cannot afford to run let's say like 25 epochs on my on the entire data set, but I'll read these 10,000 or 13,000 and so images. Resize them itself takes a lot of time. On top of that, I do not want to do 25 epochs. I'll just do 3 epochs and then see how the results looks like, and then that should be end of this tutorial. And I hope you found this to be a useful tutorial. Okay, so let's go ahead and run this. Again, I'm gonna not record this while it's running it, but I'll just show you the end result. So here is the output using entire data. And let's see, what do I mean by entire data? Like 22,000 images for training and 5,000 images for testing. Okay, so if you, again, let's look at, it's only 3 epochs. It it will get better, if you can afford to do 25, 50, 100 epochs. But anyway, the validation accuracy already started pretty high, right? I mean 82% and then 92 and so on. And the test accuracy is 89%, much better compared to what did we get the last time, 80%. Okay, so right out of the box, it was pretty good because we have a lot of images. And again, only 3 data points here, so not much to read, but at least you can see the trend here. The training accuracy is kind of saturating over there, and our validation accuracy is trying to get there, but it's not, again, very jumpy. Well, again, with 3 points, what am I saying? So this is how you can implement convolutional neural networks. Very simple, very easy. Work on your own data, and I hope you found this tutorial to be useful. So if so, please go ahead and like it, and please subscribe to my channel. Keeps me motivated to create more such videos. Thank you very much.